So next section is rotating mass type excitation. That applied force on the foundation, the Q1 sine omega t we've been talking. Sometimes it can be generated by, it can be generated by two masses. For example, this is, let's say, the motor you have, and the motor may have two mass rotating in the opposite direction. You have a mass here rotating in the counterclockwise direction, another mass in the clockwise direction. What they do is, effectively, there is a centrifugal force acting on a mass rotating. So when the two masses rotating in the opposite direction at the same time, the horizontal forces, the centrifugal forces acting on the mass, they basically cancel out. But the verticals are acting together. So the centrifugal force can be computed by the mass rotating times the rotational frequency times the radius, or in this case, it's E, from the center of the rotating point. So those two forces, effectively what they're producing is up and down equivalent force. So the force finally can be represented by here. The horizontals cancel out, but the verticals, they added together. 2 times me EW squared sine omega t. So in this case, still the vibration properties are similar, except now instead of a constant Q0 force, we have the mass Q0 represented by 2me W squared. That's the difference. So the centrifugal force given by this F, where m is rotating mass, W is angular velocity, E is the distance from center, which is eccentricity or radius. Then the two forces, when they add up vertically but cancel out horizontally, they are inward usually and they cancel out. 2me, which means one from each mass. Two of them would be added together, so it would be 2me EW squared is a vertical amplitude of motion on two rotating masses in the opposite direction. So if they are rotating in the same direction, you don't get this, because you'll have horizontal forces also. But if they are rotating in the opposite direction, the horizontals cancel out and the verticals, they get added. And that net force finally is just producing a vertically up and down force on the foundation block. And that's the same as Q0 sine omega t, except Q0 now is produced by the eccentric masses rotating in the opposite direction. If that is the case, still the general equation of motion is valid. The inertial component, the damping component, and the stiffness component, with a Q0 sine omega t, except now Q0, the constant force, is 2me EW squared. Now, if 2me if we represent it by U, then the solution of the displacement is Z cos omega t plus alpha, which has the same form as before. Now the Z's amplitude now is in the form of U. So it's kind of similar at the bottom. The only change is this U term is coming into play, and with the phase angle, which is the same as before. If you plot the dimensional non-dimension form Z by UM by M, or this, you'll find these patterns for different dampings. So this dimensionless term versus frequency ratio. Now observe that when we have rotating masses, the peaks are happening on the right side of a frequency ratio of 1. Previously, we were noting it on the left side. Now they are happening at the right side. 0.2, 0.3, which is 20% damping, 30%, 40%, 50%. So this is the pattern of motion. The non-dimensional plot shows the peak amplitude occur at W by W and greater than 1. So the peak amplitudes you see them happening at the greater than frequency ratio of 1. The angular resonance frequency for rotating mass type, you can resolve this. The damping rotational frequency is the undamped frequency divided by square root of 1 minus 2 t squared. And the peak values where the frequency are happening is Fn by square root of 1 minus 2d squared. This is the undamped natural frequency. The amplitude at damped resonance frequency, or the peak values here, you can calculate to be u by m 2d squared of 1 minus d squared. It's kind of similar, but slightly changes because now the vertical motion is produced by eccentric masses rotating in the opposite direction. Determination of damping ratio. Now, this is one thing we want to find either in the lab or from field tests. What is the damping ratio? This is a constant. And we have different materials, can be concrete, steel, or soil. We need to know what the damping ratio is to find the dynamic properties. Damping ratio D can be determined from free and forced vibration tests. We know that from damping ratio from free vibration test, if it's a free vibration, we know that there is a logarithmic decrement. The amplitude decreases gradually in successive amplitudes and finally dies out. And we already derived the logarithmic decrement, if you remember this equation, the difference between two amplitudes in logarithmic term, it's 2 pi d over square root of 1 minus d squared. If d is very small, or for very small damping, this term is almost 1. Because d is almost 0, this entire term is 1, it can be 2 pi d. This can be simplified further to show for d, you can solve this equation. D is 1 over 2 pi n ln natural logarithm z naught by Cn. Z naught is the original. Z0 is at the first cycle, this amplitude. Zn is at any point you are referring to, like Zn this point. Or you can find between the two Zn and Zn plus 1, because if you do a free test and measure these values, finally you can use this equation to find the damping value. So this is one test. You can do either a free test in the lab, or there is a way also to find it using a forced vibration test. If you do a forced vibration test using some input motion, you find for different frequencies, you record different amplitude. At some point, the whole graph, you reach a peak value, and then you pass the peak value. You'll find this property if you use a forced vibration. For different frequencies, you record your amplitudes at different points and see what peak value you have. Now, the peak, we know that it's happening at close to the resonance, or the resonance frequency, or the peak frequency. With damping, it's not exactly occurring at W is equal to Wn, but you have the peak value. But you have to multiple recordings to find it exactly or near to the exact point. If you have this data, then from this spectrum, you can find the location where the peak 0.707 of the resonance amplitude, resonance or the peak amplitude. You come to that point, and from there, find the corresponding F1 and F2. The frequencies corresponding to the 70% of the resonance frequency. If you find F1, F2, and you know the natural frequency where it occurs in the peak resonance value, if you have these three, then the damping can be found from F2 minus F1 divided by F resonance, or half of that. You can see the derivation of this equation. This is the resonance amplitude we have been talking about. From this resonance amplitude, actually, you can derive this damping equation. You can see this derivation, how it's obtained. So this is from forced vibration. We have a constant force acting on it. Or you can use a free vibration where you have initial disturbance only and find. It can be a simple test. Let's say if you have like a cantilever steel beam in the lab, you can fix it at the base. and just give it initial motion. So you see this vibrating, and at some point it dies. At two successive points, if you are able to measure, or if you know the time history of this motion, then you know from successive to successive motion you can find the damping ratio from forced vibration or from free vibration. We'll come to this point again in soil properties, I think chapter 4 or 5, where we discuss how we determine the damping ratio of soil. Now, so far we have been talking only one direction of motion. For example, the vertical motion we're considering and repeatedly considering damping, without damping, and with constant force or free vibration. But our complex foundation type, we know that we have 60 degrees of freedom system, 3 rotation and 3 translation. So there is a separate course for this, but the concepts are similar. We are merging everything into one single chapter here, but I can show you what it looks like. For vertical vibration, still you have the same equations that we talked. The inertial component, the damping component, the stiffness component, and the forcing frequency. This is like a sine or cosine function input motion. If you are talking about a sliding this way or the opposite way, perpendicular to this, for a sliding, let's say that direction is x, the equation still remains the same. The general equation of motion is the inertial component in that direction, damping component, stiffness component, and the input motion causing the motion. Or you can have a rocking motion. Rocking is against this. Let's say this whole foundation is rocking about this axis. If it's moving this way back and forth, let's say you have some angle theta. So it's just a rocking motion. If it's a rocking motion, the equations still are similar, except now instead of a translation motion, it's a rocking motion. That's why you have angular velocity, angular acceleration. Theta is angular acceleration, angular velocity, angular displacement. Otherwise, the general equation of motion remains the same. The angular moment of inertia, I naught, and the angular damping, and the stiffness component. And the input motion causing that motion, a moment which is applied on this. Or you can have a torsional vibration. Torsional is, in a sense, the whole thing is moving a vertical axis. You have vertical axis, let's say Z. About Z, you can have this torsional component, just back and forth to clockwise or counterclockwise back and forth motion. If you call that angular motion alpha, then equations are the same. Now, torsional mass moment of inertia have J, ZZ, the damping, and the stiffness in the torsional direction, and the torsional force acting on it. So the general equations of motion still remain the same, even if you have different kind of motions. For linear motions, X, Y, Z direction, they remain the same, 3. And for rotational and torsional motions, you have still the other equations. Now, for civil engineering, for example, something like for a foundation motion, we have already derived equations. For example, for a vertical vibration of foundation, Lesmer analog, still using the same dynamic equation of motion, Lesmer developed the KZ. Now you don't need to do a test to find the K or a plate load cost or something. If you have the shear modulus of the soil, if you know the radius of the foundation block and a Poisson ratio of the soil, you can find the stiffness of the soil with this equation. This is empirically developed from equations, general equations to using the soil properties. So the stiffness of the soil, for a vertical stiffness, you can this equation to find it for the soil for a circular foundation. If you have a rectangular kind of foundation, you can equivalently change that rectangle to a circular foundation and still use the same equation. And the damping, you can use this equation. These are empirically developed. 3.4 times R naught square. R naught is the radius of that foundation block. Square root of G, and this is the density of the soil. So using the soil properties, you can find these constants. The mass is the mass of the block, the foundation, and the motor vibrating on it. Damping, you can use this equation. K, you can use this equation. Q naught, this is like sine omega t. This is the input motion given from the manufacturer. Then you have the general equation of motion. So you can use the solution that you already developed. You know the maximum, the time history z. So for your foundation block, actually when you design your foundation block, you can use these equations. And you can see where you are in terms of the resonant frequency. Are you away or are you? So you can play with the G, which is the soil properties and the density of the soil. For a sliding vibration, which is horizontally in either direction, Hall's analog. This is another scientist who developed in 1967 for a sliding vibration using the same general equation of linear motion. You can find the horizontal stiffness of the soil, Kx, with this equation from soil properties. Or dx, the damping value is also given by here, or the damping ratio is given by here, or constantus Bx is also defined here. So these are previous scientists in the mid-1960s who developed for a foundation vibration the general equation of motion. So if you know the mass, the damping, and the stiffness, then you know how to find the time history of that motion or different properties. Avoid resonance, so you can design it based on that. For rocking vibration of foundation, same way. It's developed, I think, in the mid-1960s. I naught, angular momentum, angular acceleration, angular velocity, angular displacement, and K naught, C naught, and I naught can be defined here. I naught, you have mass moment of inertia, and K naught, static spring constant, and C naught, and beta naught to help you for the C naught. So you can use this. These are available in any literature, dynamic vibration property box. You can find all these empirical equations, so use them and find the general equation of motion. And with this general equation of motion, the solution is similar to what we talked already. So this is a rocking where you have theta is defined. Or if you see it in plan, this is how it looks like. These are all defined initially for a circular foundation type, but you can, any geometry, you can change it into a equivalent circular. Or for a torsional vibration, if you have a torsional vibration, you have these general equations, and the constant is defined by this. So this is just for 1 degree of freedom system. Usually if it's a foundation on soil, we treat it as 1 degree of freedom system. And this equation, you don't need to memorize anything here. All this would be available to you when you do the design. Just be aware of what the equations are, what the terms are, and what it means, the design philosophy, how to avoid resonance, what frequency you have to select, all that. Now let's come to the last section, a multi-degree of freedom systems. Multi-degree of freedom system, even if we spend so much time for 1 degree of freedom system, then the extension of that 1 degree of freedom system goes into a multi-degree of freedom system, which means you have multiple masses, multiple coordinates to define the motion of the masses. We have seen this hammering unit where a mass dropping into anvil with elastic pad. That can be represented by a mass, and the elastic pad is this damping and stiffness. Then that elastic mass is still on a foundation block resting on soil. That foundation block is right here, and the soil can be represented by a damping soil and the stiffness of a soil. So you need at least two coordinates, x1 and x2, to define the motion of these two masses. Or you can have a two-story building with the first mass defined here, and the second mass defined here. Now, horizontally, if you apply a force, P1T, P2T, then you have some displacement for these masses. You can equivalently represent this system with this. Two masses, two displacements for each mass, two forces acting on each mass, and the framing system, especially the columns now are representing the damping and the stiffness. And the mass are representing the rigid system, this rigid floor. The whole mass is lumped into the first one and the second one. So you can have just a spring mass system representing a two-story building. If you have 3-story, 4-story, it goes on. You just keep on adding masses and springs and dampers. So degree of freedom system, let's see what the general equation of motion looks like. Give me 1 second. Okay. So if you have this, if you see the free body diagram of this, now the first mass, M1, U1, you have inertial component. You have a force acting on it, P1T. You have inertial resistance on it. And also you have a force of resistance from C, the damping, which is C1, and also the stiffness, which is K1. So stiffness force, damping force, inertial force resisting. And if you see the second mass, this one, M2, there is a force acting on it, P2T. There is inertial force resisting that motion, M2, or the acceleration. And also C2, which is a resistance force, and K2, which is a resistance force, which is relative in this case, because depending on the motion of M1 and M2, this depending on this relative displacement, U1 and U2, you have a K2 force, K2 times U2 minus U1. This is a relative motion, or the relative velocity for damping. So if you take each free body diagram, now find equilibrium of motion using Newton's second law, then you can find this equation for the first mass, or you can find this equation for the second mass. Basically, the force P2 on the right for the second mass is equal to this resisting force, M2U2, M2U2, and this is stiffness and damping relative motion forces, the damping relative motion and the stiffness relative motion. The same thing for the mass one. You have these three forces acting, P1, T, C2, K2, and resisting. If you do all that, and finally, if you can represent it in matrix form, you'll have this matrix form. Or you can represent this into a compacted form like this. Now, when you say M, it's not one single M, it's a matrix. If you have two masses or 2 degree of freedom system, in this case, it's just M1 and M2. But it can be many. I can add more masses here. I can make it 10 degree of freedom system, 20 degree of freedom system. So this gets bigger and bigger. So this M is a matrix of masses times by the acceleration of each mass. And now this damping is also a matrix times the velocity of each mass. So this C you see here is a matrix of dampers. K is a matrix of stiffness. So when you have multi-degree of freedom system, this general equation is still it is valid, except now we have multiple masses, multiple dampers, and multiple stiffeners, and we put them in the matrix. For 2 degree of freedom system, you can still solve. There is analytical solution on this. You can derive this equation and find each acceleration and velocity and displacements by hand, but it gets longer. It's not as easy as the 1 degree of freedom system. It gets a little bit complicated. Now, if you have more multi-degree of freedom system, now at each mass, we can lump each mass at each corner. You may have a framing system like this. This has 6 degree of freedom system now. You have 6 masses. And same the dampers and everything. Now it gets bigger. Mass matrix is much bigger. Damping matrix is also much bigger. Stiffness matrix is much bigger. Now we are getting into a more realistic case. If you have a 10-story or 20-story building, you cannot now calculate it by hand. That's where we need computers. Now, computers like SAP 2000 or STAR Pro, that's what they do. You give them multi-degree of freedom system, they mesh it, they analyze everything, they find the mass matrix for each, the damping matrix for each, and the stiffness matrix for each, and finally the computer solve it for us. It's the same, like even if we see 1 degree of freedom system, we calculate it by hand. It was easy. We can put it in Excel or MathCAD and solve it. When it gets multi-degree of freedom system, it's the same philosophy, but the equations get bigger. The solution is becoming more realistic, and we need computers to solve it now. But the general dynamic equation is always valid. Whether you use SAP 2000, STAR Pro, even the geotechnical softwares, FLAC, everything, they are always solving the dynamic matrix, the general equation of motion. But now, depending on your mesh size, now the dampers, you'll have multiple damping matrices, mass matrix and stiffness matrix, and depending on the input motion. PT is now the input motion. For seismic, we have seismic ground motion, or externally applied load, you can have different forces here. So the philosophy remains the same. Now let's see some characteristics in dynamic behavior of some structures, like a cantilever beam. There is something called mode shapes. Last time somebody asked me how we can find the fundamental frequency of like bridges or buildings, big buildings. I said, yeah, you can run model analysis in computers like SAP or STAR Pro, and they can give you. This is exactly what they do. This is like a simple beam. Let's say it can be a pile foundation. A pile foundation now, you can assume it as a single degree of freedom system or multi-degree of freedom system. In this case, let's assume it's 4 degree of freedom system. We divided the masses into 4. Now we have 4 springs, 4 dampers for each of them. So this is a multi-degree of freedom system. So what mode shape it does is, a mode shape is a deflection pattern related to particular natural frequency. Now we're talking, when you have 1 degree of freedom system, we have only one frequency, right? When you have multi-degree of freedom system, we're going to have multiple frequencies. A frequency related to each mode of vibration. For the first mode, you have one frequency. This is like assuming it as 1 degree of freedom system. Even if you see it 4 masses, in the first mode, it's deflecting like in one direction, or like a cantilever beam deflecting like this in a static motion. The fundamental frequency for this, you can use this in analytical equation to get it. But for a second mode, now the deflection is getting more complicated. Second mode of vibration, third mode of vibration, fourth mode of vibration. You'll see more higher frequencies. SDOFS is single degree of freedom system, has only one mode shape with one frequency. That's the first one. However, multi-degree of freedoms have multiple associated with each frequency, multiple degree of freedoms, all multiple frequencies. It's not the first one. Usually we call it natural frequency. That's the dominant one. The higher ones are usually that they are not that dominant. Usually for structures, the first mode is the one which is governing everything. It's much larger. That's where we expect a resonance. But the higher frequencies still occur at higher frequencies. Higher mode shapes have higher frequencies of vibration. So n degree of freedom system has up to n mode shapes, n natural frequencies. Higher mode examples in cantilever beam. This is the first mode deflection, like in a static motion. In a static motion, it deflects in one side. But if you have more vibration, now the bending changes. We see higher frequencies. With each deflection, we have different frequencies, F1, F2, F3, F4. They occur. If you see amplitude frequency plot, you will see where each is occurring. The first mode is occurring here. Second mode is occurring around here. Third mode, fourth mode. These are the peaks. This is just to show you an example. I know you may not run SAP 2000 or STAT Pro as a geotechnical engineer, but some of you will. Because geotechnical engineering, it's an interface. You'll be designing structures, you'll be designing foundation. But when you do vibration analysis, this is what you'll be doing. Getting the mode of vibration for each, the frequencies for each mode of vibrations. Higher mode examples in simply supported beam. If you have simply supported beam, first mode vibration is like this, up, and it can be down like this, just up and down like this. This is the first mode vibration. Second mode vibration, third mode vibration, higher flexibility, higher frequencies. So these are analytically solvable. You can find them. Any book will give you what frequency for second mode, third mode, and fourth mode are for a simple beam or a cantilever beam or any beam. Concept of modal analysis. Modal analysis is a technique used to characterize how structures behave dynamically. In modal analysis, it's assumed that the complicated vibration of a structure, you may have a complicated vibration of a structure like this. This looks irregular. What modal analysis is saying is this complicated response of a structure for a seismic motion or anything is actually the sum of multiple modes. First mode is this one bending in one direction. Second mode bends like this. Third mode like this. Fourth mode, n modes, thousands of modes. When you combine all of them, it looks irregular like this. That's what concept of modal analysis said. So in modal analysis, usually what you do, you're not getting like the stresses or things like that. You are getting the mode shapes. What's the first mode frequency? What's the second mode frequency? A third mode, a fourth mode. After a few modes, we're not that much interested because higher modes, they are not that significant to excite. But the first mode, second mode, third mode, they are significant in terms of response. I'll show you later. Successive chapter, we'll see it. Even for a soil column, we'll see how the modes look like. Structures typically have many modes of vibration. As the modes get higher and higher in frequency, they normally also get more and more complicated mode shapes, and it's normally require more energy to excite these modes compared to the more simple low frequency modes. That's just to give you some foundation for what vibration looks like. I know we don't go, this chapter is wide. It's a course by itself. But I'm trying to show you the basic concept so that you're familiar to it. And next time you may do advanced analysis, time history analysis. And in those times, you'll find all these concepts. So that completes this chapter. And main reference for this is chapter 2 of reference 2, Principle of Soil Dynamics by Braja M. Das and Ziluko. But there are some sections also taken from different references, and you have them. And there is a homework specific to this chapter from reference to chapter 2, problems 2.1 to 2.10. So I want you to solve these problems independently and submit these homeworks. When you do these homeworks, you'll master the course more. This is especially an online class, and I understand some of you are following it on your phone, which is a small screen, maybe difficult to follow up. But when you go through the material, this PDF, it's self-explanatory. You can go through it by yourself with your time and do this homework, because usually homework submission is 2 weeks after completion of the chapter. So 2 weeks from now, all of you are expected to submit this. So that completes this chapter. Next week, we will start the other chapter. And does anybody have any question?